Welcome everybody. In this class, we're going to continue from where we stopped last week. In the last class, we talked about state space representation in the discrete time domain. And we talked about how to convert from the continuous time domain when you are in the S-plane. Then you convert into state space form in the discrete time domain. Then I'm going to continue from where I stopped last week. Then we are going to also do another example to reinforce the concepts we learned last week. So we know that in state space form in the discrete time domain, the representation is okay. There's a question. Will you upload this video? Yes, it's going to be uploaded after the class. So watch out for the uploaded video after the class. So we said that in state space representation in the discrete time domain is x k plus 1t is equal to ax plus bu and y is equal to cx. So it's similar to the continuous time domain. In the continuous time, this is x dot or the derivative of x, and this is ax plus bu. Then y is equal to cx. But in the discrete time domain, you are dealing with integer values of k. So k can only be integer values. So that's the difference. Then in the continuous time domain, you have the derivative. We talk about derivative, but in the discrete time domain, you use difference equation. So this is a difference equation. So the analogy of derivative is difference equation in the discrete time domain. And this should be the dimension of your A matrix. So the A matrix should be a n by n matrix. So that means that it should be a square matrix where n is the number of states. So if you have two states, the A matrix is going to be 2 by 2. If you have three states, the A matrix must be a 3 by 3. So 4 states, the A matrix must be a 4 by 4. So the A matrix is always a square matrix. Then the B matrix, the dimensions are n by m, where n is the number of states and m is the number of control inputs. So if you have just one control input and you have two states, so the B matrix will be a 2 by 1 matrix. And the C matrix, the dimension is P by N, where P is the number of outputs and N, you already know N is the number of states. So is all similar to what you have in the continuous time domain. So this is the block diagram of the state space representation in the discrete time domain. So this is our state space representation. Then we have x k plus 1t is equal to ax plus bu. So let's start with the simplest. Then y is equal to cx. So look at y is the output. We know that y is the output. So this is c. So cx of kt multiplied c times x of kt will give you y of kt. So that's what you have here. Because y is the output, is always on the right hand side. Then to represent this, we know that x of k plus 1t is equal to ax plus bu. So we already have x of kt here, but we want to get x of k plus 1t. So we need addition. We need a comparator or a summing block. So here's the summing blocks. We'll add x, a, t. So this is the A, this is the A block. So we'll bring out the x of kt. So to give us this, then we need b u of kt. B u of kt is the input. So the input is always at the left hand side, indicating that is the input. So b multiplied by u of kt is going to give us this. So we just add the output of this and the output of this together to give us xk of 1t. So this is xk of 1t. And we know that this is like z. If you convert in the z domain, xk plus 1t is z x of z, while x of kt is just x of z. So the relationship between this and this is z minus 1. So if you have z x of z, then if you apply this block that's divided by z, you will get x of z, because the z transform of the z transform of this is equal to z x of z. Then the z transform of x of kt is given by, is simply equal to x of z. So the relationship, so you have x k plus 1t here, and you have x of kt here. So the relationship is, if here is x of xz and here is x of z. So when you just divide the what is coming here with z, that's z minus 1, you're going to get x of z. So that's why we have this relationship. So this relationship, it represents the block diagram of state space form of discrete time systems. So we are going to go to another example to reinforce. So we use an application example, which is the mass spring damper system. So I've already uploaded the notes on Moodle, so you can see the notes on Moodle. So this is just another example. So given this mass spring damper system, we want to start from the first principles. So we want to first of all represent the system in equation form as a mathematical model. Then after that, we would find the state space in continuous time domain, then the state space in discrete time domain, then the transfer function in the continuous time domain and the transfer function in the discrete time domain. So that's what we want to achieve in um, this class for this particular example. So you have the mass spring damper system. So this is a mass given by M. Then this F is the external force. Then it has some two opposite forces acting on it, where B is the damping force, is the damper, then K is the spring constant. So given this system, we'll draw the block diagram of this system. Then X is the displacement. So the force due to the damper is given by Bx dot, where x is the displacement. Then x dot is simply the velocity. So it's the derivative of x, while the force due to the spring constant is given by kx. Then we want to get the mathematical model for the mass spring damper system. So we use the Newton's second law of motion. So we know that the sum of the forces acting on the body is equal to mass times acceleration. So the sum of the forces acting on the body is given by mass times acceleration from Newton's second law. And acceleration, since x is the displacement, so the second derivative of the displacement is given by the acceleration. So in place of a, we are going to put x double dot. Then this is the force acting in this direction. Then the force is acting in the opposite direction. That's why you have this minus sign. So bx dot, then minus kx. So we've been able to derive the mathematical equation for the mass spring damper system. So we want to be able to represent it in state space form. So if you are given that the states of the system, X represents the states of the system. Remember that the states of the system is what the system is currently doing. So you have two states. The first state is the displacement in the X direction, while the second state is the velocity. So x dot is simply the velocity. So where x is given by x1, then x dot is given by x2. So you have two states and you want to represent it in state space form. So we know that uh, since x1 is equal to x, then x2 is equal to x dot. So we know that the derivative of x1 is equal to x2. So when you differentiate x1, this is x1. When you differentiate x1, you're going to get x2. So that's this relationship. Then we're going to express the the equation we arrived at in terms of x1 and x2. So x dot is x2. So here this is x1 and this is x2 dot. So after expressing it in this form, we arrive at this. Then in state space form is x dot is equal to ax. X dot is equal to ax plus bu. So um, we need to get the A matrix and the B matrix. But first of all, this is x dot. So we need x1 dot. We need to make x1 dot the subject of formula, which we already did. Then we need to make x2 dot the subject of formula for this one. And you make x2 dot the subject of formula for this equation. Then you arrive at this equation. So the next step is just to put it in matrix form. So x1 dot is equal to x2. So there's no contribution of x1. The x here is 0. Then x2 is 1. Then there's no u. The input is the force. So it's going to be given in the question. So no contribution of, there's no u here. So is 0. Then for this second equation, the contribution of x1 is minus k over m, which you have here. The contribution of x2 is minus b over m, which you have here. Then the contribution of the f is the input. The force is the input. So if I represent f by u, so since it's going to be given in the question, so the contribution of u is going to be simply 1 divided by m, because you can write it this way. So the contribution of the u is 1 over m. So we're able to get the A and B matrix. Then the C matrix, if the output is given by the displacement, so you're going to be given in the question. So that means that an x1 is the displacement. So that means that you have 1 here, then you have 0 here. Then, so that's the representation in state space in continuous time. Now, we want to represent the transfer function of the mass spring damper system in also continuous time. So this is the equation we arrived at when we modeled the system. Then when you do the Laplace transform of this equation, you arrive at this equation. Then the transfer function, like you all know, is the relationship between or is the output divided by the input. So we know that the output is the displacement because yeah, it's going to be given in the question. So this is just like an application example. So I'm not like doing it in form of a question. I'm just doing it in form of like doing an application example. I'm solving an application example. So all of these are going to be given to you. So you know that the output is the displacement because I said so, though I didn't write it. Then the input is the force. So the transfer function is the relationship between the output and the input. Then this is the input and this is the output. Then you just put this formula in terms of x divided by f, then you arrive at this equation. Now, if you are given the constants for the mass, the spring, the damper, and the force, so we can express the transfer function as this. So just substituting all these values into here, we can arrive at this. Then we substitute in the state space form all these values. So this was what we got in state space form. So you substitute values for n, k, and b to arrive at this. So now I want to, because this course is discrete time domain, so we want to be able to represent the mass spring damper system in the discrete time domain. So I'm just doing all of this so that I'm starting from somewhere, then I'm going to end at the discrete time domain. So we already have this equation which we derived, and we want to convert it to the z domain or into the discrete time domain. So we want to represent the mass spring damper system in the I want to represent both the transfer function and the state space in discrete time domain. So we've done that before. So the first step is to break the equation down into partial fractions. Sorry. So breaking this down into partial fractions, we are going to arrive at this. I skipped that step. So you can just try to prove to yourself that when you break this down into partial fractions, we are going to get this equation. Then the next step is to convert to the time domain. So we have 3 steps to convert from continuous time, the transfer function in continuous time to the transfer function in discrete time. There are different approaches, but the one we majorly used, and we've done those approaches. So the first step is to break it down to partial fraction. Then after that, you convert it into time domain. Then after that, you use tables to convert to the z domain. So there are 3 steps. So the first step, we've broken it down to partial fraction. Now we'll convert this into time domain. So you will do the inverse Laplace of this. And this is the inverse Laplace of this equation above. And after converting it into the time domain, we are going to convert to the z domain. So you use your tables, your z tables, to convert to the z domain. So this is a constant. Then the z transform of this is given by this. So you just use your tables to convert. Then after doing that, you just do some simplifications, then modifications, then we arrive at this. And so we have been able to successfully convert from the S domain, from the continuous time domain to this discrete time domain, which is given by this. So if you are given that T is the sampling time, and if you are given that the sampling time is equal to 0.01, because this is when we converted into the Z domain, because we wanted to represent the system in the Z domain from the continuous time domain. So we need T, as you would have observed, there's T here and T here. So if you are given that the sampling time is this, so you simply plug in the value of T into this equation, then doing some arithmetic and some algebra, this is going to be our final equation. So now, So these all these values I'm just calling and I'm saying you are supposed to be you're going to be given if it was a proper question at the start of the question, all these values should be given to you, but it's just when I'm solving it, that's when I'm giving those values. So which is not really appropriate. So all these values should be given before you start. You don't just assume all these values. Then you now we have the transfer function. Now we want to convert in state space form from this transfer function. We want to convert it in state space form. So we did that last week, and there are some steps involved. There are up to 3 or 4 steps involved in converting from the Z domain, a transfer function in the Z domain into the state space form. So if you can remember last week, the first step I said was that you're going to divide this equation by the highest power of Z. So the highest power of Z is Z squared. So if to say the highest power of Z was Z raised to power 3, then we're going to divide by Z raised to power 3. But the highest power of Z is Z squared. So you divide both sides of this equation by Z squared. Then we arrive at this. Then the next step, which is the second step, is to introduce a dummy variable. We just call the variable E of Z, meaning that it's the error. It's just, we just name it E of Z, giving the error, such that when you perform this arithmetic or this operation, you are going to arrive at the original transfer function. So you're going to split the transfer function into two. And after that, we are going to separate them. So now we've separated, so this was the original transfer function. Then we are separating it into two. The first one is Z minus 1, which is here. Then the second one is all the remaining terms. So now we separated it out. So Y divided by Z is given by Z raised to power 1. Then E divided by U, E of Z divided by U of Z is given by this. So we've arrived at these two equations. So the next step is to make Y of Z the subject of formula in the first equation. Then to make E of Z the subject of formula in the second equation. That's the next step. So we're making Y of Z the subject of formula here. Then these two operations is just to make A of Z the subject of formula in this second equation, which we arrive at this. Then we are moving on to the last step. So the last step is to, you'll be given the states of the system. So we've arrived at this. These are the two equations we arrived at. And these are the states of the system. So you're going to be given that this is the state of the system. So I didn't start with a question first of all. So that's why I didn't give it first. So it's when I'm solving it, that's when I'm telling you. So in the question, you're going to be given that these are the states of the system. So remember when we're in continuous time, now we're in the discrete time. When we're in continuous time, this will be given to you in the question. You'll be told that these are the states of the system. So you'll be told. So the same way, when you're in the discrete time domain, you'll be told that these are the states of the system. So it could be, the question could change, but in this particular question, x1 of Z is given by Z raised to power minus 2 multiplied by A of Z. Then x2 of Z is given by Z raised to power minus 1 A of Z. So you're going to be given the states of the system. You're not going to formulate it on your own. So given these two states, we want to be able to represent these two equations in terms of x1 of Z and x2 of Z. So we know that Z raised to power minus 1 multiplied by A of Z is x2. So we simply represent this one as x2 of z. So if we go down, so uh, x1 of z is simply equal to x2 because of you are giving this relation that y of z is equal to x2 of z. So that's why you, sorry, is this equation I'm talking about. So because of z raised to power minus 1, 0 raised to power minus 1 e of z is given by x2. So remember, we are just looking at these two equations. We just want to put it in terms of x1 and x2. So that's what we are doing. So if you, since you are given this state, you can find the relationship between x1 and x2. And you can find the relationship between e of z and x2. So now, doing that, we know that from this state you are given, you know that x1 of z. So you want to find the relationship between x1 and x2. So z multiplied by x1 of z. So this is just z multiplied by x1 of z is going to give you x2 from this relationship, from these two relationships. So when you multiply z x2 times z multiplied by x2, you're going to get x1. So that's how we got that relationship. So when you multiply z and x1, so this is, if you multiply this, like this is z multiplied by x1, you're going to get x2. Then that's how we got this relationship here. Then for the second one, so we are just using this equation, then just expressing it in terms of x1 and x2. You're going to arrive at this. So you can just do it on your own. Then this is the last equation. Then you convert to the time domain. So the reason we are converting into the time domain is because the state space is in time domain, is not in z domain. So the next step is to convert to time domain. So this is, to convert this to the time domain is this in the time domain. I've already explained it last class. So this is the conversion from the z domain to the time domain. Then the last and final step is to put it in state space form, in state space matrix form. So this is the state space representation in the discrete time domain. So we just, sorry, I'm coming. Okay, sorry about that. Okay, so we'll convert into the time domain, which is given by this. Then after converting it into the discrete time domain, we just represent it in state space form. So this is the shortened form in state space form. Then the expanded form is given by x of k plus 1t is given by this, because you have two states, x1 and x2. Because in the question, you'll be told that you just have two states in the question. So you just have x1 and x2. Then this is your A matrix, your B, and your C. So we just need to put in the values of A, B, and C, given these equations we derived. So given these equations here, so given these two equations here, so x1 k plus 1 is equal to x2. So there's no contribution of x1. So here is 0 and here is 1. Then there's no contribution of u. So here is 0. So for this second equation, x2 k plus 1t The contribution of x1 is minus 0.9048. The contribution of x2 is 1.902, which is given by this. And the contribution of u is 0.0095, which is given by this. Then the output is x to k of t. And x1, this is contribution of x1, so it's 0. Contribution um of x2 is 1. So this example is just to reinforce what we did last week. So we are dealing with, I'm using a practical example to represent um, when you are giving, starting from the first principles of modeling, then you are able to convert the system. You should be able to represent the system in discrete time domain in state space form. So this is what we're doing. So if you compare the the results you got in the continuous time domain. So this is the state space in the continuous time domain. And this is the state space in the discrete time domain. So this is what we got in the discrete time domain here. And this is what we got in the continuous time domain. See that it's the same system, right? And it's the same values of M, of B, and of K. You have the same constants, but the matrix, the A matrix is different, is very, very different. The B matrix is so different. Then even the Y matrix too, it's different. So given the same question and it's just the same system and you want to convert from the discrete from this continuous time domain to the discrete time domain, you are going to arrive at different sets of A, B, and C matrices. So this is the end of the class for today. So in the next class, we are going to be doing this same example, but we are going to use a zero order odd. We are going to include a zero order odd in the transfer function because I've already explained the importance of the zero order odd because the zero order odd, that's the way the computer uses to convert from the continuous time to the discrete time domain. So that's the computers make use of analog to digital converter to convert from a continuous time system to a discrete time domain. So it makes use of the zero order odd, which is the mathematical equivalence of a digital to analog converter. So we are going to include the zero order odd to convert from the continuous time domain into the discrete time domain because the way we've converted it, this is not the actual way the computer sees the system. So the computer uses, like I said, it uses analog to digital converters and digital to analog converters. So a digital to analog converter is modeled by a zero order odd. So in the next class, we are going to be including a zero order odd into this transfer function. Then we are going to do the same thing we've done. So we convert from the continuous time domain into the discrete time domain. But now using the more appropriate way, so introducing the zero order odd into the circuit, and our result is going to be much more accurate because the results we've gotten here, we didn't use the zero order odd, so it's is the ideal case, but it's not actually the way the computer would see it because um, we've not included that zero order odd transfer function into the circuit. So that's what is going to be our topic of discussion um, next next week. So thank you all for joining. So the recording is going to be made available. So those people that are not around, they they will be able to they'll be able to um